The dawn of a new industrial revolution is upon us. It is a revolution that does not rely on digging into the earth for ancient carbon, but instead harvests it directly from the sky. At the heart of this revolution lies a microscopic marvel that mimics the elegance of a blooming garden: Perovskite nanoflowers. These intricate nanostructures are not merely beautiful to behold under an electron microscope. They are the engines of artificial photosynthesis, a technology promising to convert sunlight, water, and carbon dioxide into clean, storable fuels. Today on Fun Facts Online, we are going to conduct a comprehensive exploration into the world of perovskite nanoflowers, dissecting the breakthrough science, the economic potential, and the planetary impact of turning our carbon dioxide problem into an energy solution. Let us begin by understanding the dream of infinite energy and how we are attempting to mimic the leaf. For billions of years, nature has held the patent on the ultimate energy conversion technology, which we know as photosynthesis. In a quiet, daily miracle, plants use sunlight to strip electrons from water and stitch carbon dioxide into sugars, creating the fuel for life. Humanity has long dreamed of replicating this process, but with a significant twist. Instead of sugars, we want liquid fuels like ethanol, methane, and hydrogen that can power our cars, industries, and cities. This dream is known as artificial photosynthesis. Until recently, this field was stifled by materials that were either too inefficient, like titanium dioxide, or too expensive, such as platinum and iridium. However, the perovskite nanoflower system has changed the game by combining the extraordinary light harvesting capabilities of halide perovskites with the catalytic power of copper-based nanoflowers. Researchers have unlocked a pathway to solar fuels that are not only carbon neutral, but potentially carbon negative. The defining moment for this technology came with the development of floating artificial leaves. Unlike heavy, rigid solar panels that we see on rooftops, these devices are thin, flexible, and lightweight. They are designed to float on water, absorbing sunlight to generate a voltage. This voltage drives a chemical reaction at the surface of the nanoflowers, which are microscopic catalytic structures that bloom on the device's surface. The result is a device that does not produce electricity for the grid, but rather liquid fuel. It takes the waste product of our civilization, carbon dioxide, and turns it back into the building blocks of our economy. To truly understand why this technology is revolutionary, we must zoom in to the nanoscale, a realm where a nanometer is to a meter what a marble is to the Earth. Here, the term perovskite nanoflowers refers to two distinct but synergistic innovations: the perovskite light absorber and the catalytic nanoflower. Let's look at the engine first, the halide perovskites. Perovskites are a family of materials that share a specific crystal structure, chemically described as calcium titanate, or ABX3. In the context of artificial photosynthesis, scientists use lead halide perovskites, such as cesium lead bromide, because they are semiconductors with tunable bandgaps. This concept of tunability is crucial. Unlike silicon, which absorbs a fixed spectrum of light, perovskites can be chemically tweaked to absorb specific wavelengths. This allows scientists to layer them, creating tandem cells that harvest almost the entire solar spectrum. Furthermore, splitting carbon dioxide requires a significant energy kick, or potential. Perovskites generate exceptionally high photovoltages, providing the electrical shove needed to break the strong carbon-oxygen bonds in carbon dioxide. While the perovskite absorbs light to create free electrons, those electrons need a place to do their work. This is where the copper nanoflower comes in. You might wonder, why a flower shape? In catalysis, morphology matters. Catalysis happens on the surface of a material. A flat sheet of copper has limited surface area, but by growing the copper into a 3D, flower-like structure with petals, creases, and folds, the surface area explodes. The sharp edges and defects on the petals of these nanoflowers serve as highly active sites where carbon dioxide molecules get trapped and twisted, making them easier to break. Additionally, the shape provides selectivity. Flat copper tends to make simple methane, but the complex geometry of copper nanoflowers forces intermediate molecules to linger and interact, leading to carbon-carbon coupling. This means they produce multi-carbon products, like ethylene for plastics and ethanol for fuel, which are far more valuable than simple methane. Now, let's walk through the mechanism of how it works. The operation of a perovskite nanoflower artificial photosynthesis system is a ballet of physics and chemistry performed at the speed of light. It happens in 5 distinct steps. Step 1 is light absorption. A photon from the sun strikes the perovskite layer. Its energy kicks an electron up to a higher energy state, leaving behind a positively charged space called a hole. Step 2 is charge separation. The electron and hole are separated. The hole moves to the anode, or the oxidation side, while the electron moves to the cathode, or the reduction side. Step 3 is the anode reaction. At the anode, the holes need to be consumed. Traditionally, scientists use them to split water to make oxygen. However, recent breakthroughs use glycerol instead. Glycerol is a waste product of biodiesel production. Oxidizing glycerol is energetically easier than splitting water and produces valuable byproducts like glyceric acid. Step 4 is the cathode reaction. The high-energy electrons arrive at the copper nanoflower. Here, carbon dioxide molecules from the air or water solution adsorb onto the copper petals. Finally, step 5 is the synthesis. The electrons bombard the carbon dioxide, breaking the carbon-oxygen bonds and adding hydrogen protons from the water. The nanoflower's geometry guides these fragments to fuse together, forming ethanol and ethylene. The result is a device that sits in the sun, drinks dirty water and carbon dioxide, and excretes clean fuel. How do we build these complex structures? Creating these devices requires a mix of delicate chemical artistry and scalable industrial processes. To make high-quality perovskite nanocrystals, scientists often use the hot injection method. Precursors, like cesium oleate, are injected into a boiling solution of lead halides. The instant the cool liquid hits the hot solvent, nuclei burst into existence. By controlling the temperature and surfactants, or ligands, researchers can force these crystals to grow into dots, wires, or even flower-like platelets. For the copper nanoflowers, they are typically grown directly onto the perovskite device via electrodeposition. By applying a specific voltage in a copper salt solution, copper atoms stack up on the surface. The trick is to use specific additives, like amino acids, that act as shape-directing agents. These agents block copper from growing flat, forcing it to bloom outward into intricate petal-like fractals. Now we must address the economic viability. Can this compete with oil? For any technology to save the world, it must first survive the market. Techno-economic analyses of perovskite-based artificial photosynthesis paint a promising picture. First, there is a massive cost advantage. Unlike silicon, which requires high-purity processing, or iridium electrolyzers which use rare earth metals, perovskites and copper are abundant and cheap. Furthermore, perovskites have low capital expenditure because they are solution processable. They can be printed like newspapers using roll-to-roll manufacturing. This drastically lowers the cost for building factories. When we look at the numbers, the target cost for green hydrogen to be competitive is less than $2 per kilogram. Current models suggest that perovskite photoelectrochemical cells, with their high efficiency of over 20%, are one of the few technologies capable of hitting this target within the decade. The levelized cost of energy estimates for perovskite modules hover around 3 to 5 cents per kilowatt hour, making them competitive with fossil fuels, especially when carbon tax savings are factored in. Moreover, producing electricity is cheap, at around 3 cents per kilowatt hour, but producing ethylene is lucrative, at around 60 cents per kilogram. By targeting these multi-carbon products, the perovskite nanoflower system generates revenue far beyond simple electricity generation. The environmental impact is equally staggering. This offers gigaton-scale solutions. Natural photosynthesis is notoriously inefficient. Plants convert only about 1 to 2% of solar energy into biomass. Perovskite artificial leaves have already demonstrated efficiencies of over 10%, with theoretical limits exceeding 30%. Regarding land use, to remove 10 gigatons of carbon dioxide per year using forests, we would need a new forest the size of Europe. Using artificial leaves with 19% efficiency, we could achieve the same result with a land area of just 30,000 square kilometers, which is roughly the size of Belgium. Additionally, there is water neutrality. Unlike biofuels, which require massive irrigation, artificial leaves can operate on non-potable water, seawater, or even wastewater, preserving fresh water for human consumption. This technology enables a circular carbon economy. We burn fuel, release carbon dioxide, capture it, and use sunlight to turn it back into fuel. This stops the accumulation of greenhouse gases and turns carbon from a pollutant into a resource. However, we must also discuss overcoming challenges. Significant barriers stand between the lab bench and the solar farm. First is the water problem. Perovskites are essentially salts. Like salt, they dissolve in water. This is catastrophic for a device meant to float on water. Researchers have developed impermeable encapsulation layers using Field's metal or graphite epoxies to solve this. These layers protect the perovskite from moisture while conducting electricity to the copper nanoflowers on top. Then there is the lead problem. The most efficient perovskites contain lead, a neurotoxin. Leaching lead into waterways is an environmental non-starter. Science is racing to develop bismuth and tin alternatives. While currently less efficient, bismuth-based nanoflowers have shown exceptional stability and non-toxicity, making them a prime candidate for future eco-friendly iterations. Finally, there is stability. Solar panels last 25 years. Perovskites currently last months. For artificial photosynthesis to be viable, the catalytic nanoflowers must not degrade under the intense bombardment of high-energy electrons, and the perovskite must resist heat and UV light. Looking to the future horizon, imagine the year 2040. You look out over the ocean near a coastal city. You don't see oil rigs. Instead, you see vast, shimmering arrays of floating platforms. These are Perovskite nanoflower farms. They bob gently on the waves, soaking up sunlight and seawater. Pipes run from the arrays back to shore, carrying not oil, but liquid ethanol and compressed ethylene gas produced directly on the water. These farms are co-located with offshore wind turbines. When the wind blows, the turbines power the grid. When the sun shines, the nanoflowers produce fuel for the night. This is not science fiction. The components already exist. The race is now one of engineering, scaling up from the size of a postage stamp to the size of a football field. In conclusion, Perovskite nanoflowers represent the pinnacle of biomimicry. We observed the leaf, understood its physics, and then rebuilt it using materials that outperform nature's own design. By marrying the light-harvesting power of perovskites with the catalytic precision of copper nanoflowers, we have unlocked the door to artificial photosynthesis. The transition from a fossil fuel economy to a solar fuel economy will be the defining challenge of the 21st century. In this fight, these microscopic, blooming flowers might just be the most powerful weapon we have. They offer us a promise that is as poetic as it is practical, that our future energy will come not from burning the past, but from blooming in the sun.